To recap, we're trying to design a system that has a green LED that goes on when the temperature is below a certain value, goes off when it's above a certain value, and it turns on a yellow LED. And then when the temperature is above another critical value, the red LED is on. Now, in order to make this into a workable system, we would have to take a system and design it to convert the temperature to voltage. And just so you know, I'm not going to talk about that today because this could be an EE98 level project in and of itself. At the end of the semester, you should be able to understand how to do that, but right now we're not quite ready to discuss it. There's also a device called a comparator that we will need that'll compare two voltages. And this is what the schematic looks like. And there's an equation. V out equals 0 if V1 is greater than V2. And V out equals close to V battery if V2 is greater than V1. This particular comparator is you can get from Linear Technology. They even give out free samples. So anyway, let's say I have converted those temperatures into voltage, and that the just right voltage is that if it's, I'm going to call it 1 volt, and the green LED will be on. Everything else will be off. And if I'm slightly high, voltage is above 1 volt, the green LED will be off, and the yellow LED will be on, and the red LED will be off. And if you're in a high fever condition, which we're going to call above 2 volts, green will still be off. We'll leave the yellow on, and then we will turn on the red. How do we create this circuit? Well, it's the same voltage reference circuit that we've seen before, where we had 3 resistors. In this case, we're assuming it's a battery operated device and we need to minimize the current flow. And we notice that the green-yellow reference voltage needs to be a volt and the red reference voltage needs to be 2. So if I have 1 volt here, 1 volt here, out of a 3 volt battery, there's only 1 volt left. And so that implies that there's 1 volt drop across each one of these, and so we can set the resistors equal to each other, and we'll get the desired reference voltages, and we'll choose 1 mega ohm to minimize the power flow. Now this is just a simple example to show you how simple references can be used, and I know that some of you will want to see the complete system. You'll just be curious. So here would be the complete system. And let me take you around the schematic. First thing is transient 1. That means the simulation will monitor the voltages and currents for 1 second. This voltage source here, I'm calling temperature. And everywhere you see the word temperature, you can assume that it's connected by a wire, and that if this is 1 volt, then temperature here is 1 volt, this is 1 volt, and this is 1 volt. If this is 2, it's 2, 2, and 2. Now in order to do a ramp, what I do is a pulse circuit and only simulate for the length of the pulse up. Battery is the name of the battery voltage, and I've selected 3 for this example. I have 1 meg, 1 meg, 1 meg. And so RF 1 should be 1 volt and Ref 2 should be 2 volts. Now for the green on, I have Ref coming in on the positive and temperature coming in on the negative. So that means when Vref is greater than temperature, this will turn off. And when it's less than, it'll turn the temperature, it'll turn itself, and when RF is 1 is less than the temperature, it will turn itself on. And you can see that these are opposite, where if the temperature signal goes over RF1, the yellow turns on. And so the yellow and the green should never be on at the same time. And then you can see for red, if the temperature goes above this reference, the red one will go on. Now, all we have to do now is look at a transient simulation. And instead of time on this axis, I've replaced it with the temperature. So this temperature right here, V temperature, is the temperature coming out of this sensor. And so when it's below 1 volt, the LED is on. And when it goes above 1 volt, it turns off. And you can see that the yellow LED is opposite of that, or inverted, and that the red LED turns on about 2 volts. Now, how to turn an LED on with a voltage is a subject for another day. And something I want to call your attention to is, notice that the signal is either very close to 0 or very close to 3 volts. And so we can say that the signal's off here and on here, and nothing is really going on in between. That's a digital signal. And each wire in that case, if a wire can be on or off, or a voltage can be on or off, it's a digital voltage and it can control 1 bit. Now, something I'd like to ask is, do we really need the green LED? Because if the yellow is on, obviously the green must be off. And if the yellow is off, obviously the green must be on. The reason why I wanted the green LED is to have an LED that's on to show that the device is working. Now, a modification of this circuit is, obviously if 1 volt is around body temperature, 0 volts might mean you're entering in hypothermia. And so how would you change this circuit so that you would have a narrow band of good temperatures, and you could have a blue LED that meant you were getting too cold? The previous example, we were really digitizing the signal into normal, medium high, and really high, 3 voltage levels. Well, we can use this in any kind of analog to digital arrangement. In this case, if all the resistors are equal, A naught will be V reference divided by 4. This would be divided by 2, and this would be 3/4, and it's evenly spaced. More levels requires more resistors, but you get more bits. Each one of these would go to its own comparator and would be its own digital line. So there's 4 possibilities. The voltage could be between here, the voltage could be between these two, the voltage could be between these two, or the voltage could be above A2. So that's 4 possibilities. Four possibilities can be combined into 2 signals wires. So the number of bits is equal to the log of the number of possibilities divided by log 2, and you round down, and that would tell you how many bits you have. Now, something else is these steps do not have to be equal. You could have a logarithmic progression if you were trying to compress some data.